All right, everyone, welcome to week 6, day 2. Today we're going to be talking about utility functions, and building on to indifference curves as well, like I touched in last class. So the reading is pages 64 to 66. There's a few sections. There's a utility function, ordinal preferences, utility, and indifference curves. So the motivation for this is really utility is a starting point of going from economics being just kind of supply and demand to economics being modeled more advanced. So utility is kind of this imperfect solution to a really kind of a difficult problem of measuring happiness. Notice we don't really have anything to wire to your brain, and when you score a basket, you get a treat, or you get a kill in an online video game. The device tells you exactly how happy you are. That is, we can't really measure happiness. We can kind of have a survey, um, but then that's self-reported. It's not the same as having like an objective measure of height or weight or something like that. And so utility is kind of how we do our best to model this thing that we can't measure. So there are a lot of models that use utility. Supply and demand actually does, although it's just in the background, and I'll show you how it kind of integrates. And then there's a bunch of other models that if you're interested in doing more economics or applying economics to some other field like law or politics or urban planning or health, understanding those economic models can help you. And so you should try to understand utility to the best of your ability. What is utility? Like I said, all it is just a measure of your happiness or your satisfaction or your well-being that you get from doing some activity or consuming some good. You can also get disutility, and that would just be negative utility, so something that you don't like. And so what we're going to do in a lot of problems is, or all the problems that investigate an individual making decisions, we're going to assume that their goal is to maximize their utility or their well-being. This seems pretty reasonable to how humans behave in the real world. However, we can't just stop at utility. Hopefully, you've heard of the term marginal utility. And marginal utility is the additional benefit one gets from consuming one additional unit of a good. And so you should be familiar with the optimal decision making rule, which is marginal cost equals marginal benefits. The marginal benefit you get from uh, consuming another good would be the utility you get, or the marginal utility you get from that unit. So um, we usually like to think of marginal utility as diminishing. So the additional utility of additional consumption is higher at lower levels of consumption than at lower levels. And so we have Squidward over here is our example of diminishing marginal utility. So the law of diminishing marginal utility would say that the marginal utility of the first patty that Squidward eats is greater than the marginal utility of the last patty in the vault that Squidward eats. And if you've seen this episode, you know that there's this quote that says, SpongeBob goes, "It'll go straight to your thighs, and then you'll blow up." And I didn't do a great job, so if you want, you can go to this video here. But we think that blowing up is not good. It lowers utility or gives you disutility, which is bad. But with the first patty, you do not blow up, and it tastes good, and you enjoy it. And so that would raise your utility. And so we think that the marginal utility of patty one, the additional utility from you get from consuming the first patty, is greater than the last patty in the vault where you eat it and you blow up, which is bad for you. So an important property of utility is that it's ordinal. And ordinal is short for just meaning that it's ordered or kind of ranked. So with utility, you cannot say that a utility of 10 is 2 times better than the utility of 5. You can't say how much more one bundle of goods is preferred to another. You can just say whether one is better or not than another. So um, if you have some consumption that gives you a total utility of 10, and you have some total consumption of goods that gives you a utility of 5, and you know that 10 is more than 5, so 10 is better, and you have some other package that gives you a utility of 2, uh, you know that the utility of 5 is better than 2, and the utility of 10 is better than 2, but you can't say that the utility of 10 is 5 times better than the utility of 2. And so for comparison purposes, I have that the antonym of ordinal is cardinal. And with cardinal, you can say exactly how much one is preferred to another. So you can say something more about the magnitudes. Um, with our ordinal utility, we won't be able to say that 10 is twice as good as 5. We'll just know that 10 is better. And so I have this example here, which is about the utility that a dog gets for consuming different types of food. You can click it here, and it's a dog taste testing different types of food. And when you watch the video, we can say that this dog prefers chicken to Cool Ranch Doritos to green beans, but we can't say how much more the dog prefers chicken to Doritos, or how much more the dog prefers Doritos to green beans, or how much more the dog prefers chicken to green beans. And this captures the concept of ordinal utility, which is that it's just an ordering. But we can tell that the utility of chicken is higher than the utility of a Dorito, which is higher than the utility of a green bean. And I'll note, to kind of tie it into our last lecture, we can say that the dog's name is Tucker, has rational preference relations. So Tucker is able to rank every food to every other food. And because chicken is better than Doritos and Doritos are better than green beans, chicken is better than green beans. And that is our transitive property right there. And so now I want to talk more in depth about utility functions and marginal utility, and this will lean on calculus and kind of to integrate lessons from calculus. So utility functions, they just define how the amount of goods that you consume turns into how much satisfaction you get. And so this is just a function, which we've seen before in a two-dimensional plane. And so with considering some individual who only consumes one type of good, we can show this utility function in a two-dimensional plane. And you can see utility is an increasing function of consumption. That is, the total utility is always increasing in the amount consumed. It's always going up with each next one. However, we can notice that this slope is kind of leveling off here. It doesn't level off completely. It's still positive, but it starts to level off. And this is reflecting the property we would like for our utility to have, which is diminishing marginal utility. This is it in graphical form. And so we have our total utility as a function of quantity consumed. But a quick aside, we can have multi-period utility functions, and this is essentially what micro-founded macroeconomics theory is. So there's some applications, like you could have a spectator who drinks alcohol before, during, and after a football game, and how much they consume in each period depends on the price of alcohol in each period, and their utility is some additive function of how much they consume in each period. That's a micro example, and then more of a macro example would be like your labor supply this year compared to next year. It depends on interest rate and how much return you get from saving your money instead of consuming it and working, and that kind of thing. But back to our utility function. So our utility function, this is the actual function that this is. This is your utility equals the amount of Skittles that you eat, as you can see here, to the 0.4 power. And so you can see that there's diminishing utility, diminishing marginal utility as more Skittles are consumed. And I'm going to precisely define that. All right, so we want to know how much the marginal utility of one additional Skittle will give us. And so we need to know this later on when we get into, if we have one more dollar left, we need to compare the utility we would get from spending it on a basketball jersey compared to a soccer jersey, or food or clothing, that kind of thing. And so we're interested in the marginal utility. And so we're basically asking is, if S changes by a small amount, i.e. you eat like one more Skittle, in this case I have it as 10 more Skittles, what happens to your total utility? And so this should look familiar. This is the slope of the line between 2 points. And so our slope is just our change in utility divided by a change in the amount that we consume. And in this case, we have kind of a change from eating 10 Skittles or M&Ms to some increase in our utility here. So say it goes from like 2 to 3. However, uh, that kind of between 2 points approach, as you can see, we go from like 10 to 20 M&Ms, is not going to always work for us. And what I mean is, what if we want to know the marginal utility of the 50th Skittle? Not, going from 49 to 51. We want to know actually if I eat this 50th Skittle, how much extra utility will I get? And so we can't do from 50 to 50 because we're going to have rise over run. Our run will be 0 and we'll be dividing by 0, which is an undefined number. Okay, so what do we do? Well, we use calculus to find our slope, and I'm going to try to give you the intuition of that. So one approach to approximating the slope at 50 would be to use our point at 0 and use our point at 100 and say this is an approximation, the slope of line A1 for the slope at 50. Now you notice that A1 has a steeper slope than this point at 50, and so this approximation is only an approximation. It's not an exact measure of the slope at 50. And so it's steeper, so we're saying it's overestimating our slope right now. And so what can we do to kind of zoom in on what the slope is exactly at 50? Well, we can choose 2 points that are closer to 50. And so now we choose W and V, 80, 20, and we can see that line A2 slope is a lot closer to the slope at 50, although it's not exactly 50 still. So we're building on this intuition of if we pick points closer and closer to 50, then we'll get an accurate measure of the slope. Well, what does that mean when we close in all the way? Well, when we get all the way to 50, we're left with this tangent line. And so this light blue tangent line is only touching our function once, and it's touching the utility function at 50. And so the slope of the tangent line is the slope of the utility function at 50. And so what I could do is to find that slope is I can take the first derivative of our total utility function, which is u equals s to the 0.4, and I can find that the derivative of utility with respect to Skittles equals 0.4 times 1 over m to the 0.6. And this is the exponent rule of differentiation that I hope to cover in my calculus slides. And I also have some resources on the next slide to help you find the rules of taking derivatives in calculus. And so all we have to do to find our marginal utility of the 50th Skittle is plug 50 m for m, or it should be s, and that would be the slope at 50. And the slope we see of the tangent line or the function at 0.50 is 0.038. And so we can interpret that as eating the 50th Skittle gives us an additional 0.038 utility. 0.038 marginal utility. And I can actually graph out this function that I showed you, this du ds equals 0.4 times 1 over m to the 0.6, and it looks like this. And this marginal utility line is literally just the slope of this total utility line at every single point. And so you notice that we get a large, really high marginal utility for beating the first few Skittles, and then where this graph starts to kind of flatten out, this marginal utility line also starts to flatten out. Simple enough. I hope that makes sense. And so here's some resources on partial derivatives. Utility in our last slide only depended on one good, Skittles, or I had M&Ms in a few slides. However, as we go forward, what we're going to have is we're going to have utility being a function of our consumption of two goods. So say our utility is a function of how many Skittles we eat and how many chocolate bars we eat. And so we're going to need to be able to take the derivative of utility with respect to Skittles and with respect to chocolate bars separately. And so if you haven't had multivariable calculus yet, then this might seem intimidating, but it's really not. Um, I know you can do it if you can do single variable calculus. You just need to consider the variables that you're not taking a derivative of with respect to total utility as a constant. And so I hope to show you what that looks like in graphical form later on these slides, and then also give you some calculus slides helping to explain some of these. And these partial derivatives have important interpretations. So we're going to have utility depending on soccer and basketball jerseys, and we have z, w, and y are parameters that can be interpreted as our intensity of preferences. And so in our first utility function, u equals some number times the amount of basketball jerseys we consume or buy plus uh, some number times the amount of soccer jerseys we consume. We notice that the derivative of total utility with respect to basketball jerseys is just z, or the intensity of preferences. And we know that the additional happiness from having an additional basketball jersey does not depend at all on having any soccer jerseys, because this marginal utility does not have s in it or y in it at all. And so in this utility function, in one, basketball jerseys are a substitute for soccer jerseys. And likewise for soccer jerseys. Now, what if we have a function like number two? Well, we can see that the derivative of utility, or the marginal utility with respect to basketball jerseys, depends on our intensity of preferences for basketball jerseys plus our intensity of preferences for soccer jerseys times the number of soccer jerseys we have. So the utility we get from an additional basketball jersey uh, depends also on the number of soccer jerseys we have, and likewise. And so we can say that these are complements. And then finally, in our third utility function, if you can figure out how to take the derivative of this guy, then you'll see that goods are complements and substitutes in this utility function, which is probably closest to reality. However, this is more complicated and will add difficulty to our problem, and so we should be wary about how exactly we want to model the how goods are related and whether that will affect our conclusions. Okay, so last class I introduced indifference curves, and we know that all these indifference curves have equal utility at every bundle on the same indifference curve. And so if you have a lot of soccer jerseys and few basketball jerseys, or a lot of basketball jerseys and few soccer jerseys along this IL indifference low, then the amount of utility you get at any combination of these, of consuming these two goods, is exactly the same. And the middle indifference curve, IM, we know that IM has uh, equal amount of utility at every point on IM. Um, Literally, they're indifferent between any point on IM. They have the same utility. Uh, but we know that any point on IM is referred to any point on IL, because IM is farther from the axes. More, and that follows our more is better property of utility. Okay. And so notice that I mentioned we have soccer jerseys and basketball jerseys, and we're modeling utility. And so the earlier the utility as a function of Skittles that I showed you, we were only modeling two variables. Well, now we have three variables. We have uh, number of basketball jerseys, number of soccer jerseys, and we have total utility. And so what these utility curves are kind of a simplified version of this. Yeah, right? So the utility function is actually a plane in three-dimensional space, except what we're doing is we're projecting this down onto our good two and good one axes. And so kind of purple is one utility curve, blue is one utility curve, green's another, and yellow is another, where yellow is the highest. And so this is actually what's going on in the background of indifference curves. So it's kind of, you can think of it kind of like a topographic map where the contours show an increase in elevation. I should have a picture there. And we usually don't make those maps in 3D because it's kind of harder to understand the underlying data. And that's kind of similar to why we have these utility curves like this, indifference curves. And so technically what's going on in the background is we have a function of two variables. We have utility equals some function of how much Q1 and Q2 you consume. And on the indifference curve, the restriction we make is that this U stays the same for every combination of Q1 and Q2 on that curve. And so if Q1 goes up, then Q2 goes down to keep it on the same curve. And that's kind of summarized in this last point here. But anyway, I want to wrap it up here. Thanks for listening, and I look forward to seeing you in the next lesson.